Next, we will define what continuous function is. A function f from a poset d1 to poset d2 is continuous if it preserves least upper bounds of all chains in d1 and d2, which means that for all chain x in the poset d1, okay, if we first compute all the images of x in the set and then get the least upper bound of the images, then it will be the same as the image of the upper bound of the chain. Okay, let's see an intuitive description. So here is a set of elements in D1, okay, that constitute a chain of D1. Because D1 is a CPO, the least upper bound of the chain is also in the domain D1. Okay. Then let's consider a function f from D1 to D2. Okay. Then the image of the least upper bound of this chain x is actually the same as the least upper bound of the whole images. Okay, that is the meaning of the continuous function. So intuitively, the fact that a function is continuous implies two important things. One is the function f is monotone, and the second means that f preserves the least upper bound of chains. Okay, the first thing means that f is monotone, which means if this x, if some y is larger than some c, then this f preserves this order relation in the image fc fy. Fy is larger than fc. Okay, and also it preserves the least upper bound, which means that once we get the least upper bound of chain, then the image of f is actually same as the least upper bound of images. Okay, let's see an intuitive description. So here is a set of elements in D1, okay, that constitute a chain of D1. Because D1 is a CPO, the least upper bound of the chain is also in the domain D1. Okay. Then let's consider a function f from D1 to D2. Okay. Then the image of the least upper bound of this chain x is actually the same as the least upper bound of the whole images. Okay, that is the meaning of the continuous function. So intuitively, the fact that a function is continuous implies two important things. One is the function f is monotone, and the second means that f preserves the least upper bound of chains. Okay, the first thing means that f is monotone, which means if this x, if some y is larger than some c, then this f preserves this order relation in the image fc fy. Fy is larger than fc. Okay, and also it preserves the least upper bound, which means that once we get the least upper bound of chain, then the image of f is actually same as the least upper bound of images. For your better understanding, let's see some examples for non-continuous function. So first, if the function is not monotone, then it is not continuous. Let me explain why. Suppose we have this non-monotone function f, like this. So if it does not preserve the order in their image like this, okay, then what happened? The least upper bound of the image will not be the same as the images of least upper bound. Okay, so it is not continuous. So the next example shows a function that does not preserve the least upper bound even though it is monotone. Suppose there exists a chain n, which is the set of natural numbers, which is a subset of our domain, natural numbers union infinity. The least upper bound of the chain will be in the set, but outside of this chain, okay, which is infinity. Consider a function f from the domain to a simple set that only contains two elements. One is the bottom and the other one is top. Okay, we usually use this notation to represent the greatest element of a domain, which is called top. If the function behaves like this, which means that for all natural numbers, the image will be bottom, okay, but for infinity the image will be top, okay, which is definitely monotone. Then what happens? Then the function does not preserve the least upper bound. The least upper bound of the images, okay, will be bottom, but the image of least upper bound will be top. Okay, this kind of function is not continuous. Okay, so we can simply prove this useful lemma. That means if a function f is a continuous, then f is monotone. It only contains a few lines. Let's take a look at this. We will prove this by contradiction. Suppose f is not monotone, which means that for some a and b, a is smaller than b, fa will be larger than fb. Then what happens? First, fa is less than or equal to the least upper bound of fa and fb. We use this binary operator for the least upper bound of two elements especially. This operator is called join. Okay. So by definition of least upper bound, the least upper bound is larger than each element, for example f of a. Okay, so the second, by definition of continuous function, f will preserve the least upper bound. Okay, so the least upper bound of images, okay, will be the same as the image of the least upper bound. Okay, so this equality holds. Then finally, according to our assumption, okay, the least upper bound of a and b is b. Okay, so then finally we can conclude that fa is less than or equals to fb, which is actually a contradiction to the assumption. Okay, so finally f of a is less than or equal to fb, which means that f is monotone. Okay, then finally we are here to define fixed point. A given partial order set D, a fixed point of function f is an element x such that fx is equal to x. Okay, we write LFPF for the least fixed point of f such that if we apply f to the least fixed point of f, then the outcome will be the same as the least fixed point of f. And for all other fixed points of f, which is denoted by d, least fixed point of f is smaller than the other fixed points. Okay, that's the definition of the least fixed point. Then finally, this cleanest fixed point theorem tells us why the least fixed point exists and how to compute that. If f is a continuous function on a CPO D, okay, then f has the least fixed point denoted by LFP f, and it can be computed as the least upper bound of multiple application of f, which is actually bottom join f bottom join f of f bottom join and so on and so forth. Okay, let's prove the theorem. So we are going to divide the whole thing into two subparts. First, we will show that the chain actually exists in the domain, and each least upper bound also exists in the domain. And second, we will show that the least upper bound of the chain is actually the least fixed point of function f. Let's prove the first part. We will show this by induction that for all natural number n, this relation holds. Okay, how to do that? So the base case is very simple. The bottom is the least element of the CPO. So this bottom is always less than or equal to all the other elements. So is less than or equal to f of bottom also. Okay, which is very simple. The inductive case is also simple because of this monotonicity of function f. It will preserve the order between two elements. Okay, so we show that the chain actually exists by this induction. Okay, then by definition of CPO, the least upper bound of the chain is also in the CPO. Okay, so that proves the first part of the theorem. The second part is to show the least upper bound is actually the least fixed point of f. This proof consists of two parts. One is the least upper bound is a fixed point of f, and the second part is to show that the least upper bound is smaller than all the other fixed points of f. So it is the least fixed point. The first one is very simple. So we show that the least upper bound of the chain is a fixed point of f. First, we apply f to the least upper bound. Then what happens? So by continuity of f, we can show this equality. So recall that the image of the least upper bound is the same as the least upper bound of images if the function is continuous. Okay, then the rest will be very simple. Applying one more f to infinitely many application of f does not change anything. So finally, the least upper bound of the chain is a fixed point of f. Okay, the last part shows that the upper bound, least upper bound of the chain is actually smaller than all the other fixed points of f. Again, we show this by induction. Suppose an element called D is a fixed point of function f. Then we show that any element of the form fi bottom is smaller than D by induction. Okay, the base case is simple because the bottom of the CPO is always smaller than any other element. So this order relation holds. The inductive case is proved by monotonicity of f because application of f will preserve the original order between these two elements. Okay, so we will get this order relation also. And also because is this D is a fixed point of f, so fd is equal to D. So that for all n application of f to the bottom, n times will be less than or equal to D. Finally, then because of the fact that all the application of f is smaller than D, then their least upper bound is also smaller than D. Okay, therefore the least upper bound is actually the least fixed point.